Okay, today's lesson we're going to look at how a motor works and what happens when we have more than one wire in a magnetic field. But before we get to that, we're going to start with just the basics here. So what happens if we have two wires with current? They're going to both create a magnetic field, so there's going to be some sort of interaction between the wires. So we know that any kind of wire, right? So let's just start with a simple one. If we have a wire that's coming out of the page, we can use our left-hand rule to see that our magnetic field then would go around it in a clockwise fashion. So if we have one wire doing that, the question then is what happens if we have another wire doing the exact same thing nearby? So those two magnetic fields are going to interact, and it can be dangerous in some cases, like an airplane. If those things are creating a force that's not good, it could cause some problems. So we have to be really careful with two or more wires carrying current. So Andre Ampere, who later we call current for amps from him, he did a bunch of research with wires, and he figured out that the two key things were the length of the wire. So the longer the wire, the more the force was between them, the distance they were apart. So obviously if the wires are closer, they're going to be a stronger force, and then obviously how much current is in the wire. The stronger the current, the stronger the magnetic field, which then creates a bigger attraction or repulsion. He came up with a law to calculate that amount of force, but for physics 30 we don't have to figure out how much the force is. We just need to know whether they're going to attract or repel. So if we have two wires going in the same directions, let me just re-sketch that one we just did. So we have magnetic fields going clockwise around both of them. So we can see that where they're near each other, we have one magnetic field going down and one magnetic field going up. And if we think of the magnetic fields just like being a north-south magnet, we know it goes from north to south. So that side would be, the magnet would be something like that, and we'd have north and south kind of like that. So you can see that the two magnets are opposite directions. So if they're opposites, they attract. So even though the current's running in the same direction, the magnetic field is opposite, which then would attract. So any two wires that are either both in or both out, they're going to, the force between them is going to attract. Okay? We can use the same logic for the reverse. So if we have one wire going in, one wire going out, in this case, using our left-hand rule, this one would go clockwise, the outward one would go counterclockwise, and then using the same logic, we'd have a north-south magnet matching up, so those would be the same, so they're going to repel. Okay? So there's a few different ways of kind of thinking about this or logically doing it, but that's probably the simplest way, is just to think of if our magnetic fields are opposites, they're going to attract. If they're the same, they're going to repel. Okay, so what we're going to look at now is what happens if we put a wire with a current in a magnetic field. We already know that there's going to be a force acting on it using our left-hand rule. So now what happens if there's two wires in the magnetic field? So what we were getting to is what's the basis of creating a motor, an electric motor. So a galvanometer is just a simple electric motor where they both kind of do the same thing, but a galvanometer only rotates part ways. So it's like a voltmeter or some sort of device if we want to measure. It kind of would look like a speedometer. It just goes from one side to the other. Where a motor, we need it to spin around and around and around as long as we want, so it has to be able to spin all the way around. But the concept behind them are both pretty much the same. So we're going to draw a simple diagram here. We're going to use a simple diagram and figure out what's going to go on with a wire inside of a magnetic field. So in this diagram, we've got the current going up, so it's going up through A, B, C, D, E in that order. And if we use our left-hand rule, let's look at point B. So we know our current's going upwards, so you use your thumb going up. Our magnetic field would go from north to south, so your B finger would go to the right. So that means our force acting on that wire should be out of the page. So that length of wire B is going to come outwards. If we do the same thing at D, you can see the current's going to go around, so now our current's going downwards. So we put our thumb down, our B still goes to the right, but now our force finger is going to be into the page. So based on those two wires, you can see one's going to come up, one's going to go down. And at points A, C, and E, those wires are parallel to the magnetic field, and remember they have to be perpendicular, so there's going to be no force acting on any of those wires. They're just going to be doing nothing. So in our loop or our coil of wire, B is going to come up, D is going to go down. So what's that going to do? It's going to cause that thing to rotate. So this whole loop of wire is going to, in this case, rotate in sort of a clockwise kind of fashion. Okay. So before we continue, let's kind of re-examine this picture now, that what's going to happen once it rotates. So if B spins upwards and D is spinning downwards, what's it going to look like once those things rotate 180 degrees? Let me kind of re-sketch the diagram here. So our B is now going to be here, and our D is now going to be here. So you can see the way the current is, it kind of twists in the middle here, but we're still going in the same directions. So that means it's going to go up, and it's still going to be going up through B, and come around and go down through D. Our magnet doesn't change. So now if you do our left-hand rule, it's going to be the same, except at point D now it's going to be going downwards, and at point B it's going to be going upwards. So you can see what's going to happen is it's going to reverse. So once that loop spins 180 degrees and it flips around, then the forces are going to be opposite, so then it's going to spin back and forth. So a galvanometer, if we didn't stop it, it would just kind of flip back and forth 180 degrees. So that's why a galvanometer we only go up to 180 usually, and that's it. We don't go all the way around. So a motor, then, we basically have to figure out how can we get this thing to spin around and around without flipping back and forth. So before we do that, let's do a quick example. So this one is, we have a galvanometer. It tells us our length of wire is 3.8 centimeters. And inside the galvanometer, the spring is going to get pushed a certain distance. So in this case, what we want to do is we want to say, well, we have a magnetic force. We know that. It's ILB, so that part's pretty easy. We have our current, or the question is asking, what is the current? So we have ILB, and then that magnetic force inside the meter, right, if you kind of imagine like a little speedometer type of meter, that force is going to push that needle over. So that magnetic force then is going to equal to our force acting on the spring. So that means our force on the spring, if you remember from Physics 20, was kx. So all we have to do is put those two forces equal to each other, and we can solve it. So our k is 87.6. Our x distance is 0.0055. We're looking for I. L is 3.8 centimeters, so 0.038. And our B is 1.25. And we just need to rearrange and solve for I. So when we do that, we'll get 5.1 amps. So it's just a simple example, kind of like we did before, where we balance the forces and solve them. So our next topic then is, how do we get a motor to work instead of a galvanometer? So let's go back to this diagram. So if our galvanometer is just going to spin back and forth, that's a problem. We need to get the force going in the same direction to get this to spin around and around. So if you look at this bottom diagram, we don't want the directions of the force to change. We want to keep this one going downwards. We want to keep this one going upwards. So then what we need to do is we need to flip the direction of the current, right? So here our wires were twisted and our current went around that way. So if there's a way we can somehow always keep the current going to the left and around the loop, then we should be in business. So if every 180 degrees the current changes directions, that'll flip the direction of the force to keep matching it the same over and over again. So the trick for a motor then is to be able to flip the current every 180 degrees. So what we do is, on the end, let me just kind of re-sketch this diagram. So at the end of our loop, we put, instead of just having two wires, we use what we call a commutator, and we use a split ring, and I'll explain why we split it in a second. So what we do is we have this round ring on the end, and we connect our positives and negative wires to that. So that's going to provide the current, but instead of the wires getting twisted and changing, this thing is just going to touch these two rings to pass the current along. So the way it is now, we'd have our current going around the loop in that direction. Okay? So as the thing spins, so the force of that thing is going to spin, so you can see the little split ring thing in this diagram is going to start to turn clockwise. And then what happens when it gets to the 180 mark, you can see the gaps of the ring line up with your wires. That means there's going to be no longer a current going through. So the current will stop. And then once it keeps on going past that, you can see then it switches the wires. So this round part of the loop here that was touching the negative is now touching the positive, and the other one is the reverse. So we're going to basically be alternating from positive to negative back and forth every 180 degrees. So the reason we put the split in it is to stop it at 180 so that it doesn't continue. So we want to be able to alternate. And the reason it keeps spinning is due to just the momentum. Once this thing is spinning, the momentum will keep it spinning. So even though the current stops for a split second, it'll continue in the same direction. It'll touch the ring on the opposite currents, and that'll cause it to keep on going. So that's pretty much the only trick to a motor, is we just have to be able to flip the current back and forth every 180 degrees, and that'll keep the motor spinning around and around. And we can use that then to turn things like a lawnmower blade, wheels on our car, or any other kind of motor device. And that's all.